Today, we are very happy to have our own Slava Rychkov tell about supersymmetry and its absence in random field Ising. And as always, you have the ability to unmute yourself and ask questions. So thank you, Slava.
Thanks, Leonardo. Hi, everyone. Hope everyone's doing great in these difficult times. So I'll talk today about this ongoing project with Aprosim Kaviraj and Emilio Trevisani. We have one paper out last December, and we hopefully will put out a second paper soon. So without much ado, let me define the model, let me define the problem. So the random field Ising model is defined by this statistical mechanical Hamiltonian, which differs from the Hamiltonian of the usual Ising model by this extra term, which couples every Ising spin Si to a magnetic field Hi. So it's a site-dependent magnetic field, which is random. So it has its own distribution, and in the simplest version, we assume that the average value of this field is equal to 0. So there is some mean squared value, and the magnetic field on every different site is independent. So there's an independent distribution. For example, we can take it to be Gaussian on every site. So the correlation functions in this model are considered in the sense of the quenched average, which means that we first have to, let's take the spin-spin correlation function. So we take a particular realization of this random magnetic field. We compute the spin-spin correlation function with this magnetic field realization. So we, of course, normalize by dividing by the partition function for this magnetic field realization. And then once we did this, we average over the whole ensemble of magnetic fields, and this is denoted by the bar. So this quenched average is denoted by the bar. So this is the procedure, and in this setup, we are interested, for example, what is going to be the long distance behavior of this quenched average correlation functions as a function of the temperature. And we are interested if this model is going to have a phase transition. So for example, will it going to have a disordered phase at high temperature and ordered phase at low temperature? And if there is a phase transition, we would like to know if this is a continuous or a first order phase transition, and what are the critical exponents. And so this has various physics motivations. So all real materials are not perfect. There are impurities. Impurities can have their own magnetic moment. And under certain conditions, this magnetic moment can consider to be frozen. And then we land in this random field Ising model universality class. So there is a different type of disorder that Ising model can have, is the disorder in the bonds J, which is called random bond disorder. And so this random bond disorder is easier because it corresponds to a perturbation, as I will review in a second, which is not as strongly relevant as the random field distribution. So, of course, we would like to go to study these questions. We would like to go to the quantum field theory description. So we write down the simplest Landau-Ginzburg-like Hamiltonian, which has, as usual for the Ising model, the quartic potential term, and it couples the order parameter field to the random magnetic field H of X. And by the Harris criterion, this disorder perturbation is relevant because the dimension of the field phi is less than d over 2. So this is true both in the Gaussian fixed point and at the Ising CFT fixed point. This condition is satisfied. So which means that this perturbation is relevant and it changes. So assuming that there's a phase transition, it's going to be in a different universality class from the usual Ising CFT phase transition. So for the random bond disorder, we would have to consider perturbation phi squared, and this would be a less, it would still be a relevant perturbation for the Ising, but it would not be as strongly relevant as this one. And so about this particular phase transition in this model, there was a conjecture which was crystallized by Parisi and Surlas in 1979. And for the purposes of this discussion, I would like to phrase this conjecture as a statement having two parts. So the first part is that this phase transition is supposed to be described by a superconformal field theory living in d dimensions with a particular kind of supersymmetry. And the second part of the conjecture is called dimensional reduction, says that this superconformal field theory can be reduced to a d-2 dimensional CFT, usual d-2 dimensional CFT without any supersymmetry, which has the same global symmetry as the SCFT. And so if you take these two things, put them together, then this seems to suggest that the random field Ising model in d dimensions should have the same critical exponents as the usual Ising model in d-2 dimensions. So this conjecture is a subtle conjecture, so it's not quite correct, and nevertheless it's not quite wrong either. And so this has puzzled people for a long time, and it's still puzzling people. And so the status of this conjecture is that it is definitely correct in perturbation theory near the upper critical dimension, which in this problem turns out to be 6. So 6 minus epsilon expansion agrees with 4 minus epsilon expansion in Wilson-Fisher fixed point. But if you go to physical dimensions, like to d equal 3 or d equal to 4, then you find contradictions. So you find definitely that the d equal 3 random field Ising model is not the same as d equal 1 Ising model, and the d equal 4 doesn't agree with d equal 2. So you find this both by numerical simulations, and you also see in the numerical simulations that there is no supersymmetry. There's no sign of supersymmetry in these numerical simulations. So something's wrong, but if you go to d equal 5, there was more recent numerical simulations, and I'm sorry I'm not including references here, that showed that it does agree with d equal 3. The critical exponents do agree with d equal 3 Ising, and even the supersymmetry is there. So there are certain predictions, rather detailed predictions of supersymmetric word identities, which seem to be verified in these numerical simulations in d equal 5. So this is interesting, and it's also interesting that there is a related problem of the I phi cube universality class, which corresponds to the Li-Yang edge singularity. And in that case, for all dimensions, there is supersymmetry and there is dimensional reduction. So what's going on? Well, in our work, which has two parts, we started by providing new checks of dimensional reduction, which were different from other checks that have been performed so far because they followed a non-perturbative CFT way of thinking. So this is the know-how of our collaboration. And on the second part of the work, which is to appear, we would like to advance our own scenario for why the supersymmetric fixed point becomes unstable for d below 5 dimensions. So, so the plan of this talk is going to be that I will first give a quick and dirty introduction to supersymmetry, why you might expect supersymmetry in this problem. Then I will talk about part A at length. And then at the very end, in the last 15-20 minutes, I'll try to talk about point B. So let me give you a very rough and completely non-rigorous argument of why you might expect supersymmetry in this problem. And so this argument is completely non-rigorous. So it's just to get this, to get to the real beef. So let me assume, without much justification, that in this particular problem with random field H, I'm allowed to localize the path integral over phi's over field phi's to classical configurations, which means configurations solving the equations of motion with given random field H. So I just stick into my path integral delta function, which localizes to its classical configurations. And I simultaneously multiply by the determinant because I would like to count the classical configuration with weight 1. So once I do this completely not justified manipulations, I can write everything by realizing delta function, including this Lagrange multiplier field, which I call omega. And I will also write the determinant in terms of these fields psi and psi bar, which are going to be anti-commutative scalar fields. And now, once I wrote my action in this form, it's very easy to integrate over the random field H. So I can now integrate it out of my problem. So I do the integral over H, and I land on the following action in terms of field phi, omega, psi, and psi bar, and my potential V of phi. And now the claim is that this action is supersymmetric. So the supermultiplet has three fields phi. Well, I wrote psi, okay, psi bar and omega, and their dimensions are d over 2 minus 2, d over 2 minus 1, and d over 2, so differ by 1. And to see that the action is supersymmetric, I introduce a superfield phi, which is depends on the coordinates in the superspace x theta theta bar. So theta theta bar are real Grassmann variables, and it has this very simple expansion. So notice that my superspace, all my super field variables, they don't carry any spinor indices. So I only have scalars here. So this is might be an unusual superspace for high energy perspective. And so I write my action in this superfield formalism is just the integral over dx d theta theta bar. And I write the action using the super Laplace operator, which in this orthosymplectic OSP superspace is just box plus twice d theta bar. So this is a super Laplacian. In normalization, H is equal to 2. So this is the Parisi-Sourlas-Susy. It's the supersymmetry of this superspace. So it's the symmetry of the superspace. It has the super rotation parts, which is OSP d/2. And it has the super translation part, which is R d/2. That's a very simplest possible supersymmetry you can imagine. And of course, it breaks spin statistics theorem, so it's non-unitary, so that's why in high energy it doesn't play a role. But in statistical physics, it's fine. There's no problem, and the supercharges in this theory are scalars and vectors, not spinors. And moreover, at a fixed point, we expect enhancement of this supersymmetry to the superconformal symmetry, which is going to be OSP d+1, 1/2. So that's what we expect. And in this setup, the dimensional reduction takes the following form. So I take this superspace R d/2, I take inside it a d-2 dimensional subspace, which is parameterized by x equals x hat 0, 0. So I set two coordinates to 0, and I set theta and theta bar also to 0. So this is my d-2 dimensional subspace. I pick n points in this space, and I consider the correlation function of my supersymmetric d-dimensional theory, where I just place n points in this plane. And the claim is that this correlation function, this kinematical configuration, is going to be equal to the correlation function of non-supersymmetric theory living on this d-minus dimensional manifold, which has the Lagrangian. It's going to be a scalar Lagrangian in d-2 dimensions with exactly the same potential which I had in d dimensions, so v of phi. So written here.
Slava.
Yes.
But is the claim that the theory upstairs before dimension reduction has a richer set of observables, including fermionic operators, and it's only for this particular subset of purely bosonic objects that this happens? How do I think about these additional fermionic degrees of freedom in the upstairs theory?
So the theory definitely has more observables. So I'm giving here the simplest possible observable which survives in d-2 dimensions. Later, I will give the full set of observables which survive in d-2 dimensions.
Okay, thanks.
But in this very simple setup with just correlation functions of the fundamental field phi, so Parisis Sorlas gave a proof in perturbation theory that all diagrams that you can write using the superpropagator, they agree with diagrams with the usual propagator in d-2 dimensions using some identity involving integrals in superspace. And then later there were some non-perturbative Lagrangian arguments for this dimensional reduction given by Kardy and Zaboronsky. So in the first part of my talk, I would like to revisit this from the non-perturbative CFT perspective. So in my setup, I will be thinking about the superconformal field theory living in d dimensions and having this OSP d plus 1, 1/2 symmetry, which is an extension of the usual conformal symmetry. I'm going to restrict it to a d-2 dimensional plane, and I would like to find on this plane a d-2 dimensional CFT. So this story, it should remind you to the chiral algebra story for n equal 2-dimensional superconformal field theories that we are all familiar with. But for the purpose of this talk, it will be even more useful to confront this story with a simpler story, which is the story of trivial defects in any CFT. So what is the trivial defect? So trivial defect just means take any CFT in d dimensions, and then I pick a d prime dimensional subspace. I put all correlation functions in this subspace. So this breaks the conformal symmetry d plus 1, 1 to d prime plus 1, 1 times SO d minus d prime, which rotates around the defect. And so what are the features of this construction that we are all familiar with? So one feature is that every d-dimensional primary under this reduction to the trivial defect is going to give rise to infinitely many d prime dimensional primaries. And this is because if you take any, for example, symmetric traceless operator, we can set some of the indices of this operator to the orthogonal indices when we put it into the plane. And so this means that the spin L operator will give rise to spin LL minus 1 up to 0. But also there are the transverse derivatives of this operator, d perpendicular n, derivatives transverse to the plane, and all of those derivatives, when viewed from inside the plane, they will give rise to new d prime dimensional primaries, and infinitely many of them. And so this infinitude of primaries can be seen by taking a d-dimensional conformal block and expanding it as a sum of d prime dimensional conformal blocks. And this is well known and discussed by Matthijs Hogervorst in 2016 very explicitly. This sum is going to be an infinite sum with some explicit coefficients b prime, beta I. Another feature of this construction is that the d prime dimensional theory is not going to be a local theory. It's going to be a non-local CFT, and it's not going to have local conserved stress tensor operator. So it exchanges energy with the bulk, and it cannot be viewed as a theory on its own ground. So all these features of the trivial defect CFT, they have to be contrasted with what we will see for the Parisi-Surlas dimensional reduction story. So in that case, we will find that one SCFT superprimary is going to give rise to one, not to infinitely many, d-2 dimensional primaries. Another thing that we will find is that the SCFTD conformal block is going to be exactly equal to the d-2 dimensional CFT conformal block, not some infinite sum. And finally, we expect to find that this reduced CFT d-2 has to be local. So we expect to find a local stress tensor operator. So how does all this come about? And well, this actually comes out pretty easily. So let me just give you some key elements of the story. So, okay, I have to discuss a little bit the superprimaries, the structure of the superprimaries in this theory. And okay, it's all like very easy. So I will just guide you through this discussion, but it's basically you follow your nose, you take a superprimary, you expand it in theta, theta bar. So you get 4 fields, or 1 or 2 or 3 or 4, which depend only on x. And I would like to see, first of all, what is the content of a superprimary in d dimensions in terms of CFT primaries in d dimensions before dimensional reduction. Well, then I just have to take these indices of the superprimary, which denoted by A, and I have to set some of them to theta and theta bar. And if I do this, then I cannot set more than 2 indices to theta and theta bar if my original primary was traceless symmetric. And so, for example, it means that if I take a graded traceless symmetric primary of spin L, superprimary of spin L, it means that it will contain 5 bosonic CFTD primaries in this multiplet. And these are going to be given by delta L minus 2. It means set 2 indices to theta, theta bar. They're going to be delta plus 1, L minus 1. And there's going to be delta plus 2L and delta plus 2L minus 2 with this dimension. So remember about this number 5. It's going to come back to us. So now let me discuss the general dimensional reduction. So this is what Leonardo was asking, what is the general set of observables that we will have in the reduced theory. So I would like to consider some operators of d-dimensional theory, and I would like to set the points of the superspace to this plane Rd-2. But in addition to this, to setting the points in the plane, I would like to keep not all operators of my theory, but it's really important to keep only OSP 2/2 invariant states, which I'm going to call singlets. So there is this group which rotates around this defect, d-2 dimensional plane, and I'm only going to keep states which are invariant under this group. So what this means in practice is that the most general operator A that I can write in d dimensions is going to be a primary with some indices A1, AL, and some derivative of this primary, some descendant. So there's going to be a bunch of derivatives. And what am I saying here is that I have to take only the operators where all of these indices, AI, BI, are either along the plane. So this is one way to get a singlet under the rotation. Or if the right indices are orthogonal to the plane, I have to contract them with the metric of this orthogonal space. So there is this G2/2 metric which has the symmetric part and the antisymmetric part. And these are the only two possibilities to get singlets. And according to this classification, I can split the space of singlets, which is the vector space. I can split it into direct sum of the two subspaces S0 and S1, where I put in S0 all operators that I can construct without using this G2/2 metric. In S1, I put all operators that if I have to use G2/2 at least once, then I put them in S1. There is this splitting. And now, once I define you the states, I'm going to define my d-dimensional CFT to consist of all operators which are singlets. So these are all my observables in d-dimensional CFT, d-2 dimensional CFT. So why is this a natural definition? Well, because with this definition, I see immediately that it's closed under the OPE. So if I take two operators O1 and O2, and they both live in the d-2 dimensional subspace, of course, these two operators, they have an OPE within the superconformal field theory. And if I assume in addition that they are both singlets, that they are both class S, then it means that by symmetry considerations, all operators in the right-hand side of this OPE, they are also going to be singlets. And so OPE is going to be closed. So I get on the nose the axiom that we would like our CFT d-2 to have, that it's closed under the OPE. So that's very nice. But there is another very crucial property of this construction, which gives it a cohomological spirit, namely that all S1 operators actually decouple. So what it means is that a correlation function of any S1 operator with an arbitrary number of singlet operators, be them S0 or S1, inside MD-2 vanish. All these correlation functions vanish. And the proof of this property is really easy. So if you think a little bit about kinematics of all these correlation functions, you will realize that they will necessarily involve at least one super trace of this metric G2/2, and the super trace of G2/2 is 0. So that for this reason, these correlation functions are going to vanish. And it is this property which is a crucial difference between the trivial defect and the Parisi-Surlatz reduction. So everything what I said so far, like let's pick out the singlets, the closure under the OPE, it would be true also for the trivial defect, but the decoupling of S1 operators would not be true. And so now you can see why every superprimary gives rise to just one CFT d-2 primary. Well, it's like I said, we take a superprimary and now we consider its descendants. And now if we are only interested in class S0 operators, it means that we have to pick all indices in the derivatives along the plane and all indices inside the primary along the plane. Well, this just means that all of these operators are CFT d-2 descendants of the original operator with all indices set along the plane. So this is the CFT d-2 primary, the only one that we have at our disposal. Everything else just vanishes, decouples. And so, okay, so that's the main story, but there are some subtleties, namely that some superprimaries actually descend to zero. So as I said, superprimaries give rise to one CFT-D minus 2 primary, but sometimes this CFT-D minus 2 primary actually is zero, and so you don't get any primary. And this is very easy to understand from group theory, because this SCFT superprimaries, they're classified by the Young tableau of the orthosymplectic group, while the CFT primaries are classified by the Young tableau of the orthogonal group. And there are many more the Young tableau for the orthosymplectic group than for the orthogonal group. And so some of all of those Young tableau which do not exist for the SO, they just project to zero. And so in particular, if the dimension is larger than or equal to 4, then the symmetric traceless representations, they survive. They exist in D minus 2 dimensions. But if we go to D equal 3, then only scalars and vectors remain in D equal 1. And so in particular, you don't even get the stress tensor. So this is the subtlety of this Parisi-Surlas reduction from D equal to 3. Okay, so well, I haven't discussed the stress tensor, but I think I would like to skip this discussion. So it's really easy. So it's just like you apply this whatever I already discussed, and you get on the nose that the D minus 2 dimensional stress tensor, you get it as a member of the multiplet of the D dimensional superstress tensor, and it's conserved modulo S1. So this, I can discuss it later if someone asks questions. But I would like to discuss a very curious corollary of all this for the conformal blocks, because this is something we were very pleased to find when we realized that. So as I said, so those primaries those superconformal primaries which descend to a D minus 2 dimensional conformal primary, the conformal blocks are going to be equal. So for example, for the symmetric traceless representations, the conformal blocks are just equal. And this you can prove in different ways. For example, very explicitly by showing that these two objects, they satisfy exactly the same Casimir equation. But this has a very interesting corollary, because we know that the superconformal primary in any SCFT, once we decompose the superconformal primary into conformal primaries, this implies that the superconformal block is a linear combination of normal conformal blocks in D dimensions. And in this particular case, I showed you that we get 5 D-dimensional primaries, bosonic D-dimensional primaries inside this multiplet, and it means that the superconformal block in the left-hand side is a sum of 5 conformal blocks in D dimensions. And so this corollary implies that the D minus 2 dimensional conformal block is a sum of 5 D-dimensional conformal blocks, must be a sum of 5 D-dimensional conformal blocks with some coefficients. So this has not been suspected before, this connection with the Parisi-Surlas supersymmetry. So in fact, there are tons of different recursion relations that people know for conformal blocks, but this was somehow not one of them, because it's very weird. We are used to the relations when we go from D down to lower dimensions, like this infinite series of Hogervorst. And so we're basically saying that this infinite series can be inverted by a 5-term recursion relation. So once we conjecture this recursion relation, we very easily found these 5 coefficients explicitly. So it is indeed true. So it can be verified explicitly. So this is something that we found quite curious. So basically, this finishes my CFT dimensional reduction story. So the punchline here is that we didn't find any problem whatsoever with dimensional reduction. It does hold if there is superconformal Paredes-Roulas symmetry, and so the problem with the conjecture must be elsewhere, must be in the RG part of the story, and that's something that I would like to discuss in the remaining time of the talk, but I would like to pause if there are any questions about the first part at this point.
So the reduction occurs for this singlet subsector of the theory. In principle, you could imagine there are other observables in the upstairs theory, but those will not be captured by the dimensional reduction. I don't know if they're interesting, but just saying.
Yeah, that's this is the picture. The D minus 2 dimensional theory captures only the singlet sector of the D dimensional theory.
Also, does this
the D dimensional theory has more observables, but how to reconstruct them? The reconstruction of the non-singlet observables based on the D minus 2 dimensional information is it's a bootstrap problem. So it's sometimes this reconstruction is easy. For example, if you take a correlation function of 4 scalar superprimaries in D dimensions, so that function can be, since it just can be expanded into the superconform blocks, and all superconform blocks are exactly the same as conform blocks, and all the coefficients can be recovered from the D minus 2 dimensional theory. So that 4-point function is known in D dimensions, can be lifted uniquely from D minus 2 dimensions to D dimensions, even though it's a non-singlet object. But there are other non-singlet objects that cannot be lifted uniquely. And so reconstructing those is a non-trivial bootstrap problem.
Thank you.
Another question. So this SCFT in D dimensions, does that obey spin statistics, or was that this weird kind of SCFT which we didn't have spin statistics?
So the SCFT in D dimensions is non-unitary. And for this reason, it's allowed not to obey spin statistics. And of course, it does not obey spin statistics because it has some graded fermionic operators which transform as scalars under rotation. So definitely, okay. It definitely violates spin statistics. Okay.
But somehow the lower theory is unitary. Is that just an accident?
So in this particular case, for the random field Ising model, the lower dimensional theory is unitary, but one can imagine other situations when both theories are non-unitary. For example, for this I-phi cube, for the Li-Yang dimensional reduction story that I mentioned, in that case, both theories are non-unitary. All right, so let's then switch gear and let's go to a very different part of the story, which is the RG. So let us recall the status of the conjecture. So there are all of these cases for D close to 6, in 6 minus epsilon, in 5, where the conjecture seems to work. Then in lower dimensions, it doesn't work. And then there's some other cases, some other universality classes where it works. So this is a very natural scenario how this might happen. So the supersymmetric fixed point, which we discussed in the first part of this talk, so the RG flow has to reach this supersymmetric fixed point, and even if it exists. So suppose that this supersymmetric fixed point is unstable because there are some directions along the RG flow which are relevant, or which become relevant along the RG flow. And suppose that this happens for D less than or equal to 5 for the random field Ising model, but somehow it doesn't happen for the Liang. So then this could explain this whole table very easily. So this is the scenario that we would like to explore, and we are not the first people to explore this scenario. There was already there's significant literature on this problem, and in fact, one of the challenges of this project is to try to understand all valuable contributions which have already been made to this problem and somehow connect the dots and make the big picture. And that's something that we'll definitely do once we write this all up. So I'm not going to talk about literature much, but I'm going to explain, however, why is it that our way of approaching this problem brings something new and has a chance to say something new, is because we are using two ingredients. One of them is very standard and very widely known, and another ingredient which is not so widely known. So the completely standard ingredient which we have to rely upon is the method of replicas, which I review very briefly in this slide. So basically what I'm now going to do is I'm going to try to put on a more solid ground this slide that I had at the very beginning of my talk, where I completely non-rigorously argued for the relevance of SUSY for this problem. So I would like to give a more sophisticated argument for the emergence of SUSY, which, and the goal here is not just a sophistication, but it has to be an argument which is capable of checking its own self-consistency. Because there are some arguments that if they don't work, then you don't know what to do, but we would like an argument that we would like to be able to play with it and see if it breaks down, and would like to see why it breaks down. So in the replica method, so I'm using here the replica method for the correlation function in the language of correlation functions. So if I would like to compute a correlation function of a certain observable, let me call it here A of phi. So here I first just write down the quenched average definition of this observable. And now I'm going to multiply the numerator and denominator of this equation by partition function to the power n minus 1. And I'm going to take the limit n going to 0. In this limit, the denominator just disappears. And I'm left here with the replicated action, where I added to the field phi that I had in my problem, I added the fields phi2 up to phi n with exactly the same action and coupling to exactly the same random field h. And in particular, I have inside this exponential, I have the term phi1 plus dot 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 plus phi n times h. And so now in this formulation, I can integrate over h, assuming, for example, that it's Gaussian. And so I land on a different action where I have two terms. The first term is just the same for all replica fields, and the second term couples the replicas. So it's proportional to phi1 plus phi n squared. And so now you can start playing with this action, as many people have done. And for example, you can try to do perturbation theory starting with this action. And you can compute the propagator. The propagator has a little bit of a weird form. It has 1 over k squared term, and it has 1 over k to the 4th term. And you can do this. I mean, people have done it, but this is somehow, we would like to have a formulation which, for example, could show us immediately why supersymmetry emerges, where's the upper critical dimension, and where's the Gaussian fixed point. We would like to see all these things on the nose. And in this formulation, you have to, I mean, there are ways to see these things, but they are not immediately evident. You have to think a little bit. And so our ingredient that to deconfuse ourselves is based on a paper by John Cardy from 1985. And so this is one of the lesser known papers of John Cardy. It has maybe like, well, his standard paper has 200 citations. This one has only about 20 citations. But we think it should become better known, this paper. And we actually got to know about this paper thanks to a hint from Nicolas Surlas. So Cardy proposed a smart linear transformation of fields, which gives all these things that we would like. So the transformation is to change from fields phi I to fields phi omega and n-1 fields chi I, which are subject to the constraint that their sum has to be 0. And it's, well, it's a linear transformation. Okay, I could motivate it, but I'm not going to try to do it. So it's like phi 1 equals phi plus omega over 2, phi I equals phi minus omega over 2 plus chi I. I mean, you have to think a little bit where it comes from. I'm not going to try to do this, but the point is that if you do this transformation, it's kind of designed to bring the Lagrangian in the form L0 plus L1 plus L2, where L0 Lagrangian has this form which is exactly like the supersymmetric Lagrangian with which we started our discussion. You know, okay, this first part depending on phi omega, it's exactly the supersymmetric Lagrangian part. And here we have chi's, which are scalars, commuting scalars, not anti-commuting scalars, but there are -2 scalars here in the game. And since they enter quadratically, you replace -2 scalars by 2 anti-commuting scalars, and then you land on exactly the supersymmetric Lagrangian. So that's a very nice way to get the SUSY here and the upper critical dimension and everything that we have seen. But the most beautiful thing about this approach to the problem is that it gives you not just the SUSY Lagrangian, but it also gives you the error terms, L1 plus L2. And so if you don't drop these error terms, then supposedly you're not making any mistake. So if there is any problem with the supersymmetry, with the emergence of supersymmetry in this scenario, it must come from the error terms. So you have to look at the error terms and you have to check for consistency. So that's the beautiful thing here. And that's something that, as far as I know, amazingly, nobody has tried to do before our work. So at least that's our hope to try to say something new. And so what do we say? What do we find here? So I said there are 2 types of error terms, L1 and L2, and L1 terms, these are the terms which are proportional to n or to higher powers of n. For example, terms like n phi squared. Actually, these terms are strongly relevant. And so if n is non-zero, then there's no fixed point in this problem. So that's, by the way, very different from the problem of the random bond disorder in the Ising model, where the fixed point exists for any n, and you can analytically continue in n, staying within the space of CFTs. So here for the random field disorder, the problem is very different. The fixed point, if it exists only for n equals 0. So what happens is that as n goes to 0, there is opens up a longer scaling range of distances where the fixed point has a chance to emerge because all of these strongly relevant terms are going to 0. But in any case, as far as we can see, these n going to 0 terms, they do disappear. Their effect does go to 0 in the limit n going to 0. So let's just drop them. But these L2 terms are, however, key to understanding what may happen. So in fact, L2 terms, L2 part of Lagrangian, it contains a bunch of terms which are all irrelevant as long as you are in d equals 6 minus epsilon dimensions. And so there are many terms, and you can write all of them down. Like, for example, there are terms like phi, chi cube, chi to the fourth, phi omega chi squared, omega chi cube, and whatnot. Ton of terms. And so you say, I mean, what if one of these terms becomes relevant at some d? So they are irrelevant and equals 6 minus epsilon, but we don't know what kind of anomalous dimensions they get and so on. And what if one of these terms becomes relevant at some d lower than 6? Well, why nobody has computed anomalous dimension of these terms? It's almost like a no-brainer, right? It's just compute and see what's going to happen. And, nobody has done this calculation. It's amazing. Well, there's a reason. There's a reason because there are actually some things. There's some complications to be kept in mind. So so let me go through the list of complications. So first of all, I mean, there are many of these operators that you can write down, but not all of these operators break SUSY. So we are only interested in operators which break supersymmetry. Moreover, the analysis is rendered somewhat more complicated because not all of these operators we are interested in can be even written in terms of supersymmetric fields. For example, operator phi omega chi squared, this can be written and analyzed in the SUSY language. It just becomes phi omega psi bar psi, but operator phi chi cube cannot even be analyzed in SUSY language. So we have to work in the phi omega chi I formulation. But okay, we can do this. Okay, there is a more, the next complication is that we know that the microscopic theory, once we did the replica trick, the microscopic theory was invariant under permutation symmetry of replicas. And so all terms in the microscopic Lagrangian, be they relevant or irrelevant, they are SN singlets. So we are only interested in operators which become relevant if they're SN singlets. If some operator which breaks SN becomes relevant, it doesn't matter. It cannot destabilize the RG flow. So that's something which we have to keep in mind. And the other side of this coin is that actually, so I gave you some SN invariant Lagrangian here. Okay, this was this one or this one, but that's not the most general SN invariant Lagrangian that you can write down. And so this because there are other irrelevant terms which you can add to this Lagrangian, which preserve SN invariance. And so this point was stressed in a paper by Brezan and the Dominicis in '98, and this was helpful for us to understand this situation. So you have to take into account more operators. So this more general SN singlets, which give rise to more operators. So things get even more complicated. So another complication is that SN symmetry, which is very important for this problem, it is not manifest in Cardy basis. So the whole idea of Cardy was that, okay, you break SN invariance to make the Gaussian fixed point manifest. But in his formulation, there's only SN minus one subgroup of the symmetry which acts on these chi I fields is manifest. And finally, this Sn is completely obscured by Rg. So this you can already see because the fields phi, omega, and chi that they all came from linear combinations of field phi I, which were permuted by Sn, but they all have different scaling dimensions. So how can this even happen? To understand how such a thing can happen takes significant effort. And so we think we have everything under control. So we think that we can take all of the salts into account. So we have a picture. And as a result of all of these calculations and thinking, we have a concrete scenario that I would like to present. So we actually identified a particular operator in the random field Ising model, which satisfies all the conditions that you expect the operator, dangerously relevant operator, to have. So it is in a sense singlet, it breaks supersymmetry, and it becomes relevant for D less than a critical dimension that in our approach, based on some two-loop calculation, we estimate to be 4.1. Of course, this number has to be taken with a grain of salt. Okay, it's just a two-loop calculation, and it might change. It can become 4.5, for example. But it seems, fortunately for us, it seems like in a good range of dimensions between 4 and 5. So what is this operator? This operator is omega chi cube. Well, it's not gonna tell much to you, but the important thing is that it's not the most obvious operator, because the most obvious operators that you can write down, they don't satisfy some of these conditions. Like either they are not singlets or anyway. So there is this operator that it's not like the first operator you would look at. For example, the operator that might seem more promising is phi chi cube, because phi has lower dimension than chi. But phi chi cube operator is not a singlet, so it cannot be important for this problem. So we computed the dimension of this operator to two loops in epsilon expansion, and it doesn't get actually a one loop contribution, it gets a negative two loop contribution, and so it becomes relevant at 4.1. Okay, so far so good. This looks promising. We did the same thing for the branched polymers for the I phi cube, and in that case, following exactly the same methodology, we see no relevant Sn singlet. So all operators we see, all Sn singlets we see, they get positive anomalous dimensions, or of course this is a perturbative calculation, but still we don't get any obvious inconsistency. And so that's where we are. So we would like to present this scenario, and hopefully it will stimulate the discussion of this curious problem. And I would like to finish this talk by presenting the smoking gun of our scenario, because there were other scenarios which have been advanced, but we think that this smoking gun can probably help to distinguish our scenario from other scenarios. Is that a consequence of our scenario is that the supersymmetry can be actually realized in this problem. So as I said, the four-dimensional numerical simulations in the random field Ising model, they did not detect supersymmetry, and they did not detect dimensional reduction. But our prediction would be that by a particular tuning of the disorder distribution, or by a particular tuning of the disorder coupling, so for example, by changing h phi to h phi plus I phi cube with a particular value of alpha, it should be possible to tune the phase transition to the supersymmetric fixed point also for d equal 4 dimensions. So this is seems to be an unequivocal prediction of our scenario, which might be one day its vindication. So this is my last slide, and this will be my last minute. So I think I'll stop here. Thank you.
Thank you very much, Slava. So any questions?
I have a question. Hi, Slava.
Hi,
so this operator O, which is the one that takes you away from this fixed point, in the case that you're just, say that you're only in 6 minus epsilon dimension, there's an operator in the ordinary Wilson-Fisher fixed point 4 minus epsilon dimension, which has the same dimension as this, right? Am I understanding correctly this correspondence between the two fixed points?
No, this operator does not. That would be great, actually. I mean, thanks for this question, because that was one of our first ideas. We thought, okay, I mean, we know all dimensions of all operators in Wilson-Fisher, so can't we just like go through the list and see if there's like some operator which does something weird? But this omega chi-cube operator, it does not have any counterpart in the Wilson-Fisher. So Wilson-Fisher only describes the supersymmetric part of this fixed point, which means like all operators that you can write down using, first of all, the operator has to be, it should be possible to write it down using psi bar psi, which means that it should be basically only chi squared, but not any other power of chi. And in addition, it has to be a supersymmetric operator. So even it has to be only particular linear combination of omega phi and chi squared, these kind of things. And this guy is not one of those. So we just have to compute it independently.
Okay, thanks.
Slava?
Yes. Who is asking that? I don't hear your question.
Sorry. Can you hear? How different is your operator from the one that we found by using, you know, several replica sector, and which has exactly the same behavior of being equal to 0 at 2 loop when you're below 5 dimensions? Can you relate the two operators?
Gilles, so I should, yeah, I'm sorry, Gilles, I should have mentioned that there was a lot of work, interesting work on the subject by Gilles Tarjous, who I'm happy is attending my seminar. And so a big challenge for us is to relate what we did to what they did, and much of what they did was using functional realization group, but there was also some calculation of the epsilon expansion. And as far as we can see, it's not the same operator, but we have to look more carefully into this. And
okay, thank you.
And we intend to do this before we publish our work. Thanks for the question.
May I ask, Slava, you have identified one operator which breaks through Z and which becomes relevant. Are there others? Have you tried all others are irrelevant?
Thanks, Eduard, for this question. No, in fact, I mean, we tried, of course, several operators, but in this, so there are some things that help you to classify, to reduce the computation to finitely many checks. So let me give you some examples. For example, some operators which are supersymmetric. Okay, for supersymmetric operators, there's not much you have to compute because their dimensions you know based on the dimensions of the Wilson-Fisher, and you know that they're all going to be irrelevant. So that's nice. then you go to the operators which break supersymmetry. So the operators which break supersymmetry, they're classified by whatever remaining symmetry they preserve, because there are some subgroups of supersymmetry that may be preserved. For example, there is a subgroup of super translations that some of the operators preserve. And then there are some operators which break super translations. So this omega chi cube operator, it breaks super translations, if I remember it correctly. So if the operators, they preserve the same symmetry, then presumably there's going to be some level repulsion phenomenon. And so if the lowest operator stays relevant, which preserves certain symmetry, or stays irrelevant, so I wanted to say. So suppose that there is a certain super translations and the lowest operator stays irrelevant, then the higher operators, they're going to be repulsed from the lowest operator. And so they're not going to cross. And so presumably, if you believe into this no level crossing phenomenon, then you might have to compute, at least in the epsilon expansion, only dimensions of the low operators. And that's what we did. Okay, we will try to explain our logic when we write the paper. But we didn't find any other operator which becomes relevant in the interesting range of dimensions. That's interesting. That's curious, because there could be more than one.
Eduard, we're not hearing you. You should unmute yourself.
When you discussed L1 is supersymmetric only at n equals 0. So there is a correction term proportional to n there as well. Did you consider that?
Well, so it's the story of n equals 0 is in our picture. So that's something where we see a difference between. So we read your paper, and the part where you discuss the importance of this other singlet operators, which are not the most obvious ones, we completely agree with you. But then there is another part of your paper where you argue that the limit n going to 0 may not necessarily be smooth, that there could be some terms, some correction terms, which are proportional to 1 over n.
Yeah.
So, of course, if such correction terms are present, then then the story becomes extremely more complicated, because we cannot drop L1, because L1 is proportional to n, but if there is some effect which is 1 over n, then it's going to compensate L1, and then we have to take this into account. However, that's something where we disagree with your conclusions. So we think that in using this Cardi basis, it becomes somewhat easier to trace these factors of n, and perturbation theory becomes like with like a usual Gaussian fixed point and so on. And so, in particular, the Gaussian fixed point itself that we have is completely non-singular for n equals 0. And so we don't see any enhancement, 1 over n enhancement using Cardi basis.
Good.
And so for this reason, we believe that these L1 terms, they can be safely dropped.
Good. Thank you, Slava. It's very nice.
Any further questions? So perhaps I have a question. So the idea is that you're predicting the existence of a supersymmetric fixed point, for example, in 4 dimensions, but that would be unstable. There would be some relevant flow which breaks supersymmetry to the actual theory that describes this disordered system in 4D. Is that the prediction?
Yeah, the prediction is that in 4D there are two fixed points. There is a supersymmetric one. Supersymmetric fixed point clearly exists in 4D because we can just take a supersymmetric Lagrangian, just as a pure quantum field theory exercise, take a supersymmetric Lagrangian in 4D and start this flow. It's going to flow to the supersymmetric fixed point in 4D. That's clear. So the supersymmetric fixed point does exist in 4D. So in 4D, we predict that there are two fixed points. There is a supersymmetric one, and there is a non-supersymmetric one. If you just tune one parameter, for example, the temperature, then you flow to the non-supersymmetric fixed point. This is the usual phenomenologically relevant flow that people have observed in Monte Carlo simulations, presumably.
But the supersymmetric fixed point is presumably solvable, right? Because it's just the uplift of the two-dimensional Ising model.
Yeah, it is. The supersymmetric fixed point is solvable.
So can you just not go there and identify the relevant operator that would bring you to the
not the full supersymmetric fixed point is solvable because because there are some operators. This is weird. This is the part which is kind of weird, because the operator which makes you flow away from the supersymmetric fixed point, it seems to exist in some different different field bases which does not include the fields of the supersymmetric fixed point. That's some mind-boggling feature of this problem that I don't yet find the right language to describe. The supersymmetric fixed point is not fully solvable, meaning that only supersymmetry I think, yeah, I'm not sure if the supersymmetry break-in deformations of the supersymmetric fixed points can be reconstructed using just the two-dimensional Ising model information.
Got it. Okay, so there were many questions. If
I have a remark.
Please,
Hello?
Nicola.
Yes. So I would like to point out the work also of Imbri and Bridges. And this is a rigorous work, and they show the problem of branched polymers, that there is dimensional reduction, but not only on the critical point, but also far away for the critical point. Are you aware of this work?
Of course, I'm aware of this work, but I also would like to comment. I think this work is usually completely misunderstood by the community. So let me say a few words about this work. So there is a famous indeed paper of Bridges and Imbri who. So there was this problem of dimensional reduction for branched polymers, and what Bridges and Imbri found is that they found a very smart model of branched polymers, which is supersymmetric at the microscopic level. Just imagine a lattice model. Well, it was not a lattice model, but it was just a particular microscopic realization, actually a class of microscopic realizations of branched polymers, which were supersymmetric on microscopic level in presence of a cutoff. And then for that particular class of models, they showed dimensional reduction. And everyone is ecstatic about this result, but in my opinion, this result doesn't clarify anything about the branched polymers, because they have nothing to say of why dimensional reduction holds for branched polymers, even for those models of branched polymers which are not supersymmetric. So if you just take any random model of branched polymers, it's not going to be supersymmetric. So supersymmetry is an emergent phenomenon also for branched polymers. And their result has nothing to say about why supersymmetry is emergent for branched polymers. They have no control over supersymmetry break-in deformations, even infinitesimal ones. So I think even for branched polymers, there's still a lot to be understood for this problem. So the fact that their rigorous result has closed this problem, I disagree with this interpretation, which is usually present in most of the reviews. So thanks, Nicola, for this, for giving me the possibility to.
Slava, may I ask again? I'm sorry. Assume you are in 5 dimensions and you can do experiments in 5 dimensions. Apart from checking that the critical exponent are the same as 3 dimensions without random field, are they word identities of SUSY that you can check which show that the model experimentally would be supersymmetric? What would you check apart from critical exponent?
Well, certainly there are other things that you can check, and this was this recent nice work by Marco Pico, by Nicola, by Giorgio Parisi, and by Fitas. So what they did is that they took they took, say, 5-dimensional random field Ising model in a interesting geometry which had some dimensions. So it was a finite lattice which had some finite extent in 3 dimensions, and it had a much longer extent in the other 2 remaining dimensions. And in this finite volume setup, the supersymmetry implied certain relations between, not just by critical exponents, but for example, for normalization of certain quantities between connected and disconnected of critical finite volume correlation functions. And no, they were critical, but they were finite volume. So this goes beyond critical exponents, and they found that in 5D it agreed perfectly. Some quantities, finite volume quantities. It's really pretty remarkable test of SUSY at a high precision level, at a better than 1% level in some of the cases. So it's pretty amazing work.
Okay, so
I have a question.
Yeah, sorry.
I mean, your operator, which you say makes the fixed point unstable, is omega times the sum of the chi-I cube. So if you're to go to the end of Cardi strict, then you replace the chi-I by a fermion, but you can't have fermion cube because you have only two fermions in the game. So how do you?
How do I deal with this operator?
Yes, I mean, what is this operator if I use fermions? And does it exist?
It does not exist. So it's one of these operators. The only way I know how to compute is to keep general n and then take n going to 0 at the end of my calculation. But this operator is not evanescent. So it's for example, there are some operators that you could try to write down. For example, if you try to write down the operator sum chi squared squared, so that operator, in terms of fermions, it would become psi bar squared, and we know that psi bar squared is 0 in terms of fermions. And if you try to do this calculation in n dimensions, you will see that this operator chi squared squared, it just goes to 0 identically if you send n going to 0. So it definitely does not exist. But this chi cube operator, even though I don't know how to write it down in terms of fermions, I would love to be able to, but I don't know how to do this. I do the calculation for general n. I compute correlation functions with this operator. Then I take the limit when n goes to 0. I get some finite quantities. So this operator exists. So we do
everything means from
what it means
what it means in my language.
in your language.
So
Yeah, because I have an operator also which breaks supersymmetry, so it must be rewriting, must be way of relating this to it.
Yeah, well, I'll have an appendix about that. It's a complicated story, but there are some people talk about breaking SUSY. For example, there's like a ton of papers talking about spontaneous breaking of SUSY in this problem. I don't understand what this means. Why spontaneous? It's just explicit breaking of SUSY. It's not spontaneous. It's just, yeah. Well, anyway, don't get me started.
it seems that the discussion is getting a little on the technical side.
Yes.
So I think, of course, I invite you guys to continue it offline. In fact, if you like, I could just leave the Zoom chat on and you can continue, but I think it's probably preferred some privacy. You don't want to be broadcast to the whole world. So, well, thank you very much. It was a great seminar. There were more than 120 participants at times, and it's amazing to see that basically the whole community of people working on this old subject tuned in. So maybe something good came out of this crisis. And we'll continue this series. Stay tuned, and we'll post the next seminar soon. And thanks, everybody. Bye.
Bye.
Thanks for having me.
Thank you, Slava.